Have you ever wanted an LED matrix on your earlobe? No? Well, let's make it happen anyway. Following my LED industrial piercing, we were left with these 0201 LEDs, which are so small that inhaling them is a very real danger. We also found these off-the-shelf LED stud earrings. So the idea for this project was simple really, just replace that single LED and plastic gemstone with as many 0201 LEDs as we possibly can. It just so happens that I was playing with LED matrices not so long ago for the volumetric display. Quite a few people asked me where I got this matrix from, and the answer is I made it. It was designed in KiCad, ordered from China, and then assembled on my pick-and-place machine. It is unusual to be able to justify having a pick-and-place machine in your house. This isn't mine, I've borrowed it for a very specific project, which I will post eventually. But that board has dozens of unique components, and loading these reels takes ages. Once the machine is set up, it can crank out circuit boards like there's no tomorrow, but that initial setup is what takes time. For that reason, I wouldn't normally use this to build a one-off circuit board. But the thing about an LED matrix is that it only has one unique component, so setting up the machine to produce it is as quick as it could possibly be. The solder stencil was made on my K40 laser cutter, and in a sense, this machine is the K40 of the pick-and-place world. I've only borrowed it, but I looked up how much it cost, and really that is very cheap for an industrial robot. On the other hand, it's little more than a glorified 3D printer. It picks up components with a vacuum nozzle, holds them over a camera, and uses OpenCV to find the outline to correct their position. There was no reason not to produce several of these boards. One of them went to the volumetric display prototype, and the rest we can do whatever we like with. I recently started playing around with the CH32V003, that's the very cheap RISC-V microcontroller, and so for fun I wired up one of those to it. Here's a little animation made in Blender. The chip only has 16 kilobytes of memory, so we can't store much video data on it. We can extend that by reducing the bit depth. I've given it a bit depth of 4, which you can't really see. After gamma correction, it doesn't equate to much. We could put this all on a board and make loads of them for very little money. The microcontroller is like 15p, and the LEDs are less than a quarter of a penny each. What could we do with hundreds of tiny, self-contained LED matrices? Potentially, we could cover a jacket in LEDs, with matrix boards arranged like plate mail. I'm not sure how you'd address them, or maybe you don't need to address them if the animation was cell-based and it just passed a signal to the neighbouring boards. It could be very cool. Well, for now, all I've done is stick a battery and a pin on the back to turn it into a badge. This is directly inspired by Mike Harrison's flashing LED badge, which is far more clever than what I've done here. If you want more details on this, I've put a page up on my website, mitzella.com/badge. But what this video is supposed to be about is the earring. The reason I'm showing the badge is that it demonstrates some of the difficulty of doing an LED matrix on a 2-layer board. We have a grid of wires and a series of row and column connections. That means that putting any components on the back is very difficult because you just have no room to route anything. I've managed to cheat here and squeeze the battery connection in between the traces. But that's only possible because it's one big pad, there's no fine pitch connections. The badge has a 3mm pitch grid of 0603 LEDs. For the earring, we're going to try and do a 1mm pitch grid of 0201 LEDs. And we're also going to try and put the microcontroller on the back. We don't want any other parts on the front, and we don't want a thick border. I was not even able to do a basic layout of 0201 LEDs at 1mm pitch within a 6mm process. These wires have a drill diameter of 0.25mm, so we've already pushed ourselves into the second price category, and there is no way we can possibly put parts on the back of this. Adding more layers doesn't really help. One option is HDI, that's with blind or buried wires, but then we're looking at a significant cost increase, hundreds of dollars just for a small run. And the cheapest HDI stacker still isn't ideal for what we want to do here. Ideally, we want staggered blind wires, which is of course possible, but it's the kind of thing you need to request a quote for. I've no idea how much it costs. So to keep things within our hobbyist budget, let's construct our own 4-layer board with blind wires by sandwiching two 2-layer boards with interconnects as a land grid array. We've got 2 designs in the same panel, and the panel has symmetrical mounting holes. The LED array is just that. The outline is 9mm in diameter, and the back of it brings the row and column connections to a series of 0.5mm pads. The other board has a matching set of pads. It deliberately only aligns in one orientation, and this supports the rest of the circuit, which consists of just our CH32V003 in a 3mm square package. These big pads, and I use the term big relatively since they're 1mm in diameter, these are power, ground, our 1-wire serial debug, and the reset pin just for the sake of it. I got a proper solder stencil this time, because at this scale the kerf of my laser is inconsistent. It's not expensive to get a framed stencil, and you can put several designs in the same thing. I'll start by building another one of these badges, so I can demonstrate the process for a normal circuit. This is solder paste. It's a mixture of powdered solder and flux. We line up the stencil, and then squeegee the paste onto the board. When the board is this small, it's hard to avoid the stencil bending, so I've not done a very clean job of that, but the whole reason we use this process is because in general it's very forgiving. Next, we clamp the board in the pick-and-place machine, and if we want to be really fancy, we can calibrate the position of it. I step through the first couple of components manually just to check everything's okay. Picks up the part, visually confirms how it's holding it, and places it on the board. When we're ready, we just go for it. This footage is in real time, and the machine is running at 50% speed, so it can go twice as fast if we dare. I've also told it to only use one head, but if we mounted the same vacuum nozzle on both heads, then we could double the throughput that way. And for a board like this, we don't even need the vision, so if I turned off the visual checking, that would hugely speed it up too. But as it is, it took just under 2 minutes to make this board. And for the final 2 parts, I can't be bothered to load the wheels into the machine, so I shall place these by hand. I do have a reflow oven, but for your viewing pleasure I'm going to do it with a hot air gun, so you can see what happens. The beauty of solder paste is that the capillary effect fixes most alignment problems. Everything just magically snaps into place. The downside of using a heat gun is that it's easy to overheat parts. You can see the top of the switch starting to melt. And here's a close-up of the result. Despite my messy stenciling, the result is pretty much perfect. So easy! So cheap! Now let's do the same thing, but 3 times smaller. Here are the boards, and the first step is to sandwich 2 of them together. I forgot to film this process, but here's a picture of the stenciled paste on one of the boards. I just placed one on the other and reflowed it. We could have done this with a higher temperature solder, so it's less likely to come apart when we reflow this repeatedly, but I didn't think it was likely to be a problem. I built the first circuit off camera. For the second one, it's now even more difficult to check the stencil alignment. I even added fiducials to the panel, but forgot to add them to the stencil. While the first one stenciled reasonably well, it left a residue in the holes, which I found very difficult to clean. I probably should have gone for a thinner stencil and used a finer grade of solder paste, or even just to clean the stencil properly. I think the way to do it is just soak it in isopropanol and then clear the holes with compressed air. In the interest of laziness, I decided to plough ahead with, however one could politely describe this mess. It's a bit too small to be doing manual corrections, but that didn't stop me from trying to dab more solder onto the worst offenders. This will work, it just may not be quite as uniform as the first one. Onwards and into the machine. It's not in shot, but I'm using another one of the boards at the other end of the clamp to keep it parallel. I'm calibrating using the vision system, which has the capability to be quite accurate, but this interface makes it very difficult to be precise. To be fair, we are operating well beyond the stated spec of the machine, so maybe this would normally be considered good enough, but it would be much easier if we could just type in the numbers instead of having to hold down a jog button. I fitted the very smallest vacuum nozzle, and unlike the others, it seems to have an oblong shape. The head has full rotational control of the nozzle, but there isn't normally a zero position, it's just a smooth magnetic collet, so all I did was visually line this up with the orientation of the parts. The nozzle does appear to be able to pick up the O201 part, which wasn't clear before I tried it. After placing the first component, we then need to worry about polarity. The only way to check this is to get out a magnifying glass and look for the cathode. Another problem I encountered is that the parts are so small they would jump out of the tape. As the tape is advanced and the protective film is pulled back, that causes quite a bit of vibration, and some of them just ping off and are never seen again. The pick-and-place machine is able to detect when it hasn't picked up a part, and has 3 reattempts before giving up and asking for help, which is kind of cute. The thing that made it reliably grab these O201 parts was altering the position of where it picks them up. There's an offset parameter, and I just made sure it picked up the part as close as possible to the bit where the film is peeled back. The default distance is 4mm. The vision system does seem to be acknowledging the outline and correcting for it. It's interesting that this machine doesn't actually know how big any of the parts are supposed to be. It just draws a box around whatever it sees, whether it's an O201 LED or a 48-pin microcontroller. I originally had some problems with stray light affecting the cameras, but I fixed that by adding some black tape around them. It's nice that you can click step to advance slowly. It takes 4 steps to place a part. But at some point we need to stop being a pussy and just go for it. It's interesting that in that tray of stray parts next to it you can see a SOT23 component, which is the same size as the AT-Tiny 9 used in the Charlie Star project. I remember when that was considered small. Here we can see how it's placed the parts at a 1mm pitch. It's pretty impressive. I reflowed it with the hot air gun, but got a little too close and one of the parts blew away. I fixed this with a pair of tweezers, but unfortunately put my hand right in front of the camera. It's because of that uneven solder paste that the grid now looks a lot more wonky. But so long as they work, I don't care. The wonk is only visible under a microscope. Now we go for the third and final round of stenciling, placing the part, and reflowing. I'm doing this on a fiberglass mat with the vague aim of stopping the rest of it from heating up too much. The heat from the heat gun is very one-sided, so it's not really a problem. To this we add some wires, and finally, the display springs to life. This display is tiny. I'm mainly doing this for the technical challenge to see if building something like this at home is possible. And I'm not going to complain that that was too easy, but that was a lot easier than I expected. While I cut this out of the frame, we do need to think about what we want it to display. The spinning triangle is cool, but was only meant to be a test. It's very difficult to get this to appear on video the way it does in real life. Under the studio lights and a macro lens, it seems somewhat mundane, but it's like this magical tiny disc with a very bright LED display on it. We could make it scroll some text? It is mesmerizing, but not really the aesthetic I was hoping for. Another option is blinking lights, where the phase and frequency of each blink is randomized. They start out together, then devolve into a chaotic sparkle. Well, the good thing about this one-wire debug protocol is that it's possible, albeit fiddly, to reprogram this even after we fully assembled it. So we can delay all our decisions until the very end. let's prepare the stud. Start by yanking out the gemstone, and inside of there is a tiny circuit board. It's got one LED and one resistor. Those need to go, so I'll attack them with a soldering iron. We've got a lot of room in there, so I decided to add some capacitors. Possibly not necessary, but certainly won't do any harm. There are so many things I could do to make this less fiddly. But that looks fine. Continue. We trim and tin the wires on the back of the board, and then gently coax them into the desired positions. When I built the first one, it was at this point that I found it didn't work. See, that tiny alkaline battery is perfectly capable of lighting up one LED, but I don't know why I was surprised that asking it to light up 52 LEDs and a 48 MHz processor didn't work. The circuit was just drawing too much power, and the chip kept rebooting. I dropped the power usage significantly by lowering the clock speed to 1 MHz, and also lowering the duty cycle for the LEDs right down to less than 1%. And let's be honest, the original LEDs were far too bright. We want something that people want to look at, not shield their eyes from. Finally, we need to set the circuit within the prongs. And if you want to learn about gemstone setting, this video is probably not the place to look. I'm just using a pair of tweezers and my fingers, but it's very hard to get this on camera. Jewelers have invented various ways to hold earrings while you're working on them, so next time I will try and do it properly. And with that, you would think the earring is complete. Unfortunately, during my setting attempt, I slipped and knocked off one of the LEDs, which is obviously unacceptable, so some rework is in order. At times like these, I do sometimes resort to wrapping thin copper wire around my soldering iron and shaping it into a disposable tip. You need to wrap this very tightly if you want it to work. This is gauge 21 wire, or about 0.7mm diameter, so we need to file it down to a point. Start by removing the remains of the broken LED. Give it some flux. Yes, I do occasionally use flux. And this particular situation seems to call for dual-wielding tweezers and soldering iron. Nice. Given how fragile the display is, I should probably give it a dollop of epoxy for protection, but I'm not sure I can be bothered. Further signalling my extreme laziness, I 3D printed a slightly modified copy of the case that I made for the industrial piercing. Then you can stick the two earrings inside like that. I don't know how clearly this came across so far, but I'm not fully convinced anyone would want to wear these. They're a fantastic technical achievement, but not necessarily a fantastic bit of jewellery. They also don't have a particularly good battery life. With the more expensive SR521 coin cells, you'd get maybe an hour and a half of use. Ideally, light-up jewellery should last for a whole evening. I guess I could make the LEDs even dimmer, but the way to really extend battery life is to have the animation reactive. Instead of on all the time, it would only respond to music or movement, etc. I am pleased with the tiny display though. I'm thinking it doesn't have to be an earring. It could be a cufflink, or a shirt button, or even a false fingernail. Do we want LED text scrolling along our fingernails? I don't know. Having said all that, it wasn't hard to convince my talented ear model to don these earrings and show them off being worn. Once I get the hang of stenciling it cleanly and reliably, I should be able to churn out tiny LED matrices quite easily. So I will have a think about what the best direction to take this is. I do, however, have a large backlog of video footage to edit. I need to carefully split my time between doing new interesting projects and documenting things I've already done. As always, there is plenty more information and source code on my website, mitzala.com.